Hello, happy Monday and happy start to semester 2. We're halfway to 8th grade. Congratulations to that. All right, we've got two problems today that are looking at extending our understandings of balances and equations and really making sure that you can use the distributive property in a way that's going to let you manipulate equations and expressions. So for the first problem of the day, you were given a rectangle. And with this rectangle, you had not super obvious side lengths. You needed to do some reasoning around how those side lengths could be determined. And then I gave you two different people's claims. One person claimed that the area of this rectangle could be represented by the expression 5 times, in parentheses, 8x plus 3, while the other person said it could be represented by 40x plus 15. And I wanted to know who, if either of these people, did you agree with, that they actually represented the area. So I said that the lengths weren't immediately obvious because in this large rectangle you have these two smaller rectangles. And so in terms of thinking about what 8x and 3 would actually represent, you need to consider that this is in fact one long side. So if you're going to calculate the length of that one long side, you would need to add those two lengths together. So you actually have a large rectangle that has an area of, a side length of 5 and a side length of 8x plus 3. So then we need to think about what it means to calculate the area of a rectangle. And you could think about columns and rows, and this would lead many people to also remember what they've done in the past. That would be that the area of a rectangle could be calculated by multiplying the length and the width of that rectangle. And you need to have the length and the width kind of connected because that's how you can talk about rows and columns. We're not talking about parallel sides, we're talking about perpendicular sides here. So to look at this first one, is this going to represent area? Well, I have a length of 5 and I have a length of 8x plus 3, and those are being multiplied together. Does that match what's going on here? Up here, I have a length of 5 and I have a length of 8x plus 3. And if I multiply them together, that would be how I would find the area. So in fact, this does work. We've got length, we've got width, we've got area. How about this one? What might be going on here? Well, it helps that this rectangle is already broken up into two smaller rectangles. If I wanted to calculate the area just of this rectangle, I would take my length of 5 and my smaller rectangle's width of 8x. 5 times 8x would give me an area of 40x. To calculate the area of the other small rectangle, I would need to make sure I know what this length is. Well, parallel sides are going to be the same in a rectangle. They're congruent. So I would take 5 times 3, and that would equal 15. In order to find the total area, I would need to combine those two areas, which means I would need to add them. So it looks like 40x plus 15 does actually work because I have the area of the rectangle 1 and I also have the area of the rectangle 2 that are being combined. Both work. So what if the area is 95? And we know that the area of this rectangle is 95 square units. What would x have to be in order to make that true? Well, I have a choice. I could use my parentheses guy that looks at the whole rectangle, or I could use the one without parentheses, which is looking at the two smaller rectangles. I'll do it both ways because students did it both ways. We could say, on the one hand, that 5 times 8x plus 3 needs to equal 95 because we know that the area needs to be 95. And then on the other hand, we could say that 40x plus 15 equals 95. I'm going to go through them one at a time. Looking at this one, it looks like a number trick would do the trick here. I could use a balance, but then I would really have to expand anyway, so I might as well just use a number trick. So if I have my secret number x, and I multiply it by 8, and then I add 3, and I end with my multiplication of 5 because that's outside the parentheses, I'm going to need to end up with 95. To undo this, I'm looking at inverse operations. So instead of multiplying by 5, I now need to divide by 5, which tells me that this would have had to be 19. If I subtract 3 to undo adding 3, I would now have 16. And if I divided by 8 to undo multiplication by 8, I would have that x has to equal 2. On this side, I could do a balance or I could do a number trick. Since I just have the x on one side, a number trick might be faster. So let's see. I have x, I'm multiplying x by 40, and then I'm going to add 15, and I'll end up with 95 as my area. So to undo the addition of 15, I would subtract 15, working backwards, that puts me at 80, and then if I were to divide by 40, working backward, that puts me at x equals 2 as well, which is great that the two things both work. Now, if I wanted to go above and beyond and check it back in, and some people immediately could tell that x was 2, they just looked and it fit in the equation, I could do that. I could say, well, 40 times 2 is going to be 80. 80 plus 15 is 95. So x has to be 2. Doesn't matter which equation I use. So, we had a couple notes. First note, the distributive property, which is like if you were distributing, if you are kind of putting things in places. The distributive property is it shows the relationship between multiplication and addition. So in the case of the rectangle that we had, I just realized I'm really far away. In the case of the rectangle that we had before, with 5 times 8x plus 3, we could get that to equal 40x plus 15. Some people notice that a shortcut here is you can just distribute or multiply the 5 through. 5 times 8 would give you 40x. 5 times 8x would give you 40x. And 5 times 3 would give you 15. So you've got some different options. You can think about it as groups, like with the balances, people did multiple groups. You could also think about it as area like this. You also have a shortcut. Lots of different ways that you can consider the distributive property. So let's use that for the second one. I've got two rectangles, and they have the same area. First rectangle has a width of 4 and a length of x5. And the other one has a width of 3 and lengths of 2x and 5. These two have the same area, which tells me that the area is going to have to be equal for the two. I've got an equation kind of already ready. So looking at this, if I wanted to be thinking about area as length times width, well, I could say I have a length of 4, and I have a width of x and a width of 5, and putting those together, it would be x plus 5. And that needs to be equal on this side to a length of 3 times 2x and 5 combined. That would give me 2x plus 5 would be the total length there. I can't add further because this is like saying I have 2 bags and 5 pennies. That's not something that I can put together because I don't know how much is in each bag. So this is my equation when I haven't expanded it out. To expand it out, I could say 4x plus 20 is equal to 6x plus 15. And to check that up here, this smaller rectangle would have an area of 4 times x, or 4x. This rectangle here would have an area of 4 times 5, or 20, 4x plus 20. And over here we would have 3 times 2x and 3 times 5. And that fits down there. Now, just for giggles, let's use a balance and solve it, since we haven't done any balance work today. And cap my markers so I don't waste all my ink. Alright, so I know that 4x plus 20 needs to be equal to 6x plus 15. If I set myself up a balance, I know that I need to have 4 bags and a weight of 20. And on this side, I need to have 6 bags and a weight of 15. What do I see if I'm trying to get x by itself? Well, looking at what I could take off of both sides, I know that I could take only 4 x's off. Since this one has more, this is my limiting factor here. So I can take 4 x's off on this side. Got to keep it balanced, so I would do the same over here. Now I've gotten rid of all my x's on this side, so let's focus on the pennies. 15 is my limiting factor, because I don't have any more than that while I have 20 here. So if I took 15 off this side, I would need to take 15 off this side, which would actually leave me with just 5 left over. And that would leave me with 2 bags that need to be equal to 5 pennies total. If I split that up, I'm going to have that x needs to equal 5 halves or 2.5. And just to see what that looks like in the algebraic method, if I had 4x plus 20 is equal to 6x plus 15, first thing you say, let's take 4 x's off of both sides. I'm only looking at x's, I don't care about pennies right now. So I have now no x's over here, just 20. And then I have 2 x's and 15 pennies. Then we were going to take 15 off of both sides. Doesn't have anything to do with the bags. So now I will have 5 is equal to 2 x's. And then I want to get x by itself, so I can divide by 2, so I have just x, which means that x is equal to 5 halves. And that works there too. Okay. So you'll see that every time we're doing something with this algebra here, we're layering in. How can you work with more and more complex equations? I am continuing to push students to think as well about contexts. How could you write equations when you're given a certain situation? But we're going to talk more about that after Friday's concept test. I'm really going to be looking for students to be able to solve equations, and we're going to talk more about how you can build equations given a context afterward. All right, please reach out. Concept test on Friday. Have a great night.